So we'll move to the fourth talk. So Daniel will be talking about key stretching and deniable encryption on mobile. Sloth.
Yeah, cool. Let's quickly wait for the slides. Hopefully this works. Yes, that looks good. Cool, let me start the timer so I don't overrun too much. Hi everyone, my name is Daniel. I'm going to present to you Sloth, which is a set of algorithms and schemes to do key stretching and deniable encryption on smartphones using secure elements that are already there and without any modifications to the operating system. Starting with hopefully not a very controversial motivation, local password authentication is still needed. It's the only method we have that provides full deniability, something that we don't have with biometrics and hardware tokens. Those can be forced against the user's will. And most importantly, for smartphones, it works offline, which is great. But we all know passwords come with a few hurdles and issues. Users tend to choose relatively simple passphrases that can be guessed and brute forced. And if we generate passphrases for the user, they tend to be long and hard to remember. See, for instance, this Bitcoin seed passphrase consisting of 12 words. Not many of those we want to remember every day. And that's where a concept called key stretching comes in. The idea is relatively simple. We start with a low entropy key, run our deterministic algorithm, and out comes a more secure key. The low entropy input could also be a passphrase, and the idea is by making this algorithm computational intensive, we mitigate some of the brute force risks. And importantly, those algorithms kind of have a parameter, some difficulty that we can tweak to make it more difficult and harder to brute force. So these key stretching algorithms are slow and inefficient on purpose, and we have different variants. We have computational ones like PBKDF2, and we have some that only run if you have a certain set or a certain amount of memory like Algo2. However, an adversary can still gain an advantage by simply using more compute. So as an adversary, if I have 10 times as many computers, I'm 10 times as fast. And if I throw even more money at the problem, have a supercomputer, have GPUs, have custom chips, then I still have an advantage and can brute force passphrases quicker. An alternative to this is to use an online interactive approach. So imagine you have a server somewhere in the cloud, then that server can enforce, for instance, timeouts or rate limits. But the problem here is the adversary would, or an adversary that observes the network traffic can still learn when we use a certain feature. That's something we might want to hide. And also, it no longer works offline. Luckily for us, modern smartphones have something that's called a secure element, or Apple calls them secure enclave. We just abbreviate them as SE and solve both problems at the same time. And the idea is we basically have a little private server in our smartphone that we can communicate with. And it's protected against physical attacks, so we can rely on it to, for instance, store keys securely and do cryptographic operations. And conveniently, they've been equipped with, for instance, authentication attempt counters and can enforce timeouts. So you might have seen that if you try to unlock your phone, it will block for a certain time. That's all enforced in hardware. Well, that sounds too good to be true. And unfortunately, as average app developers, we're not allowed to use these nice features because the operating system doesn't give us access. So we're stuck with just like normal cryptographic operations. And we don't have too much to choose from. So on Android, we can do some symmetric cryptography, some asymmetric cryptography. On iOS, it's even less that we can access. So we were sitting down and trying to think really hard, okay, how can we still make this work? And to remember basically all we want, we start from a low entropy input, do some computation, have a key on the other end. And for Android, we leverage the secure element in a particular way that we call long sloth. So what we first do is we take our passphrase and hash it to a pseudo-random bit string of a certain length. Then we feed that as input into the secure enclave, run for instance HMAC on it with a secure key that can't be extracted. And on the other side, what we get as output, we just post-process to meet the key size that we want. And the nice insight is, well, in the beginning, when we do our pre-computation, we can just make it longer. So the HMAC has to do more work, takes more longer time, and it's more difficult to do. And this SE is now basically a bottleneck. No matter how much compute the adversary throws on the left and right-hand side of this bottleneck, they cannot speed up the process. So that's quite nice. And what we can see when we play with this input length, we actually get quite nice predictable timing. So on the x-axis, you see the payload as it increases, and then the duration is almost linear on most models. So we can really pick a point on there that we're interested in. And as I said, iOS is a bit more grim, so we can only do elliptic curve operations, some signing, some Diffie-Hellman key agreement. So how do we solve this? Well, the good news is at least the key agreement has very predictable timing. So a single operation has a single amount of time it takes to run. And now our idea is, basically what we do is we hash our password into multiple variants that are depending on the password. Each of these variants we map to a public key. Then with this public key, we do individual key exchanges with a secure element. Importantly, it's not parallel hardware, so all these ones sequentially, and then we hash them so that all of these steps contribute to all bits of the output. And so an adversary would have to run the entire thing for every password guess to check if the password, for instance, unlocks a certain ciphertext. And what we do here is we no longer make the input longer, we just increase the number of colors in our little rainbow here to make it computationally more expensive. And what we can do with this now is basically we can set ourselves a certain time guarantee. For instance, we want to make sure it takes at least 60 milliseconds, and then we can find parameters that moves us to the right there. And this is a big step up from what we have with normal key stretching, where it just makes it quote unquote harder, adds more complexity. Now we get definite time guarantees in milliseconds. And if we, for instance, have a low entropy passphrase, for instance, we choose 3 words from a word list, and we choose a certain minimum runtime, for instance 6 milliseconds, that means the adversary would have to spend at least 100 years to try all combinations. And that's really nice. And it doesn't matter how much compute they have, how much money they throw at the problem. So this is quite neat. And we can go from long passphrases to really short memorable ones. And I hope this is no stuck in your brain. So banana, water, strawberry, that is, for instance, a passphrase that would keep your data secure. And I hope you might agree that that is quite easy to remember. And you might approach me tomorrow if you remember the passphrase and might have some chocolate to give away. So why do we need this? Why are we interested in local password authentication? So one really interesting use case is plausible denial encryption. And the threat model on a high level is, for instance, like this. You have a journalist which has some sensitive documents on their phone. And they have a benign password that unlocks some landscape photographs, and then they have the secret password that gives access to the sensitive documents. And in our threat model, there's a capture event where the adversary comes in, and they get access to the smartphone, so they can look at it with technical means. That's where our secure element physical protection steps in. They can try to coerce the user to unlock it. That's where our safe password comes in. And they can try to brute force the password. That's where Sloth comes in. This threat model that I described is what we call single snapshot adversary. They have just one moment in time, and then from then they try to break, and the journalist knows and doesn't touch the device anymore. But in real life, we might have a different threat model that we call multi-snapshot threat model. And there the adversary might take snapshots. For instance, the phone backs up data to the cloud, and the adversary then has all these snapshots also to work with. And one common vulnerability in this setting is that they can observe when ciphertext changes. For instance, the ciphertext in those snapshots would only change if the content of the encryption changes. So we want to make sure that the adversary doesn't even gain this information. How do we do that? Well, we wrap it into another layer of encryption with a key in the secure enclave, and then we rotate that key in the secure enclave, making sure we have different ciphertext as we go along. This is a very quick summary of it. I would refer you to the paper for a bit more details on also why we need to have that key in the secure enclave and not outside of it. All of this we've implemented for Android and iOS, so long sloth, rainbow sloth, and hidden sloth. It's ready to use as packages. If you are keen to try that out. It works on basically all iPhones and a lot of modern Android phones. And there's more in the paper, so we started looking a bit more onto how to formally analyze those algorithms with all-time guarantees on secure elements. So if you work in that area, that might be interesting to look at. And we have more technical details explaining why we have to do some things in a complicated way because the APIs are not really great to use. Yeah, thanks a lot, especially also to our reviewers. This went through a few rounds, polishing it. And if you take some things away from the talk is that for plausible deniability, we still need local password authentication. We can build really nice key stretching schemes with secure elements that don't need any changes to the operating system. We can add nice protection against multi-snapshot adversaries, and if you build anything in this space, you can use it already today. Thank you.
Okay, thank you, Daniel. Questions for Daniel?
So if you were allowed to use those APIs that are blocked from you, what would make it a whole lot easier? Would it make it completely easier? Would you be able to expand on it and make it faster? So on and so forth.
I mean, if I get full access and can even write software on the secure element, I can make anything happen, right? So you can make sure that after a certain number of attempts, the underlying key is erased, or that the timeouts increase with every try. So, for instance, as you see it, for instance, with the iPhone and Android phone, all these things are very nice to do. There are good reasons though why we don't have those APIs, right? So the secure element usually has limited storage in it. So for instance, the iOS has a certain number of counters they can use, and then Apple of course says, well, we have our operating system services that need these counters for device, encryption, etc. And the other thing is, it's kind of nice that the code that runs on these things is relatively small, and we don't supply any user code, because then of course everyone in this room gets really nice research ideas of running little apps on there, doing side channel attacks on the secure element itself, which makes securing the thing way harder. But yeah, if we get access to nice secure element or something like open Titan, the open risk or low risk chips that are being built, then that opens a whole range of new great ideas that we can implement.
Thanks so much.